Okay, welcome to the presentation on efficiency. So efficiency is basically a ratio of the amount of useful energy that we're getting out to the amount of energy that we're putting in. So the amount of energy you put in is going to be equal to the amount of energy coming out, but not all of the energy coming out is going to be useful. So for example, if we have a light bulb, okay, let's see if I can draw me a light bulb here. Okay, we pump 100 watts of light in, okay, so we get light, or 100 watts of light in. How do you pump light into a light bulb? We pump electricity in, 100 watts of electricity into the bulb. We get light out, but we also get heat. Sometimes we get sound. So we don't always get out exactly what we're looking for. And that's exactly the reason why our newer bulbs can use, for example, 12 or 14 watts, maybe 14 watts of power, and put out the same amount of light. But they don't put out as much heat, which means if you grab a 100-watt light bulb after it's been running for a while, it's extremely hot. The air around it is hot even. Whereas maybe an LED doesn't get near as hot. It's not to say it doesn't get hot, but it doesn't get near as hot. So what does that mean? LEDs are more efficient. So LED light bulbs are more efficient at converting electricity into light. Okay. Now, if your goal is to have light and heat for some reason, well, an incandescent light bulb might not be a bad choice. But what we're looking at is the power out divided by power in. Now, the main thing here is that you never get, this is like, I want to put a big star by it, that you can never get an efficiency that is greater than 1, ever. You can never do it, okay? So, don't if you get an efficiency that's greater than 1, you did something wrong. Most likely what happened is you need to flip these two terms, because that's probably what you did. You didn't realize what was actually power in was power out. So that's important as well. Sometimes it's not super clear either. So, but let's just look at a pump. So let's say we have a pump here, and we have pressure gauge or flow meter and a pressure gauge. If we look at the flow, okay, we look at the pressure. Let's say we get 10 GPM. We get, I don't know, 1,000 PSI. Okay, we can use these two terms to find power. In this case, I'm going to say hydraulic horsepower. So we can do pressure in PSI times GPM divided by 1714 equals horsepower, right? And then, of course, we can look at the amount of torque and RPM put on this. So torque is, let's say we've got some torque times some RPM divided by torque is to be in inch-pound, and divided by 62,025 is going to equal to mechanical horsepower. If we look at the point between here and here, okay, this would be power in, and this would be power out, okay. We can look at the amount of power we're getting out is going to be less than the amount of power we're getting in. Why? Well, because the pump is not going to convert our power into pressure and flow exactly. Some of it's going to go into heating the fluid up, creating noise. If you've ever heard a hydraulic pump run, a lot of them run very loud. Some of them are not, are pretty quiet, but especially some of the big, brand new ones that are like variable displacement. But for the most part, old fixed displacement pumps are pretty loud. They make a lot of noise. They heat the fluid up. So that energy being converted to light, heat, sound, that's all energy that's getting taken away from being converted into pressure and flow. So there's going to be some efficiency. Okay, by looking at the difference between power in these 2 points, between our power out and power in, we can, if we divide that out, we can find our efficiency. And the main thing here is these two powers are in horsepower. You can have power in horsepower. You can have power in watts and kilowatts. You can do it in many different ways, but the main thing is efficiency is a ratio. It is a unitless number, which means whenever you're dividing, your 2 units cancel out to have no units at all. Okay? So that's basically, this slide is saying exactly what I was saying. You're going to measure between any 2 points. For example, taking pressure and flow rate measurements, and then the mechanical energy being put out in this case was what this is referring to. But with hydraulic systems, we have 2 other types of efficiencies. We have volumetric efficiency and we have mechanical efficiency. Now, volumetric efficiency is the ratio of actual distance divided by theoretical distance, or theoretical volume divided by actual volume. So, if we look at a cylinder, okay, we have, let's just say we have some displacement, okay? So this is a displacement, this has an area, okay? If we have area times displacement, we get a volume, right? Another way of looking at it is area times height, right? If our volume of fluid that we put in doesn't create the distance that we expect that the cylinder will move, then what happened? Well, the fluid didn't just disappear. What happened is it leaked around the seals. Now, on a cylinder, this doesn't happen very much, okay? Volumetric efficiency of a cylinder is great. Absolutely wonderful. Now, what we're going to talk about here in a second is mechanical efficiency, and they're not always great mechanically, but they are definitely very good volumetrically. But pumps can have low volumetric efficiencies, especially something like a gear pump. We're going to talk about gear pumps here in a little bit, a couple weeks. Gear pumps that are worn out have horrible volumetric efficiencies. In fact, that's the way that gear pumps get worn out, is that over time their volumetric efficiency gets worse and worse, and eventually you're putting a ton of power in and getting almost nothing out. And that's because they have bad volumetric efficiency. So basically, it's the ratio of the what you expect to get in the distance on a cylinder versus what you're actually getting, or the volume. You can do it by volume, you can do it by distance. Either way, remember, efficiencies are always less than 1. So if you get greater than 1, you don't always know what should be the distance, what should be distance in, what should be this. Just look at your ratios. Remember, you're never going to get an efficiency less or greater than 1. It's always going to be less than 1. Mechanical efficiency. Now, mechanical efficiency is basically, if we look at this cylinder again, okay, let's say that to move a load, let's say our load is, I don't know, let's say it's 2,000 pounds. Okay. And then to move, let's say this has an area right here. Actually, here. Area, we'll say this is equal to 2 inches. So you're like, okay, well, what's the pressure required? Well, if you do 2,000 pounds force divided by 2 inches, you're like, oh, well, I can do that. That's 1,000 pounds per inches squared, right? Easy peasy. But if you actually if you measure this, you take a pressure gauge here, you put a pressure gauge on there, and it says, hey, my pressure is 1,100 psi. You're like, what the heck? it's requiring 1100 psi, and it's only moving a 2,000 pound load. That 1100 psi should be moving what 2200 pounds, right? What happened to that extra 200 pounds? Well, that's actually caused by friction. Remember, a cylinder has got seals everywhere, okay, lots of places. You have seals around the piston, so there's seals here. There's piston seals. There's wipers. There's seals at the where the rod exits. If there's two rods on it, if there's a rod coming out the other end, you've got seals over here, right? So everywhere there's a seal, that's a great thing because it increases your volumetric efficiency. Good seals create good volumetric efficiencies, but they also create friction, and friction, it decreases our mechanical efficiency. So again, we can use force or we can use pressure to find our mechanical efficiency, but either way, you're going to have a mechanical efficiency less than 1, okay? Main thing, if you don't know which is which, you'll eventually, over time, you'll figure out which should be which, but the easiest way, you're never going to have an efficiency greater than 1, so. And then our overall efficiency. So we can get our overall efficiency by looking at the horsepower out. So for a cylinder, our horsepower could be something like, be equal to like velocity times our force divided by 550, right? And velocity would be in feet per second, and our force would be in pounds force. And then our pressure could be horsepower. This is a power out, by the way, horsepower out. So our horsepower in would be hydraulic horsepower, which would be pressure in PSI times volume. So this is a PSI. And this is GPM divided by this constant 1714. Okay, so this would be our power in. So our power in is always going to be greater than our power out. Okay, so we can find total. This is if we do our volumetric efficiency, total would be equal to our power out over power in. But there's another way. If we know the volumetric efficiency, we know the mechanical efficiency, then we can just multiply these two together. Okay? And multiplying efficiencies is something we do quite often because let's say we know the total efficiency of a pump and the total efficiency of a cylinder. So we know the total efficiency of a pump. We know the total efficiency of a cylinder. We multiply them together to get the total system efficiency. Now, there's a caveat to this because if I tell you, if you take the pump efficiency, you take your cylinder efficiency, you're going to get your system efficiency. There is other things that cause inefficiencies. For example, line losses are going to be an efficiency loss. Anything like a hydraulic load, like an orifice or something, is going to create some system efficiency or some inefficiency in the system. So you have to take those things into consideration. But if you've got two components hooked directly together with very little line losses in between, this is not a bad way of estimating system efficiency. And you can get these efficiencies by looking at spec sheets, especially for pumps and motors. There's tons of spec sheets out for those. For cylinders, not so much, but you can still find some of the efficiencies for those, depending on the cylinder. Alright, so we have a cylinder receives 1 GPM of pressure at, 1 GPM of flow at a pressure of 1500 psi. The diameter of the cylinder is 2 inches. And this is where I have totally forgot to add in the force and the volumetric flow rate. So, or velocity actually. So, you can't solve this by these two. We're gonna take those two out. This is a messed up problem here, but we'll the force is gonna be equal to 4,500 pound force, and our velocity is gonna be equal to 0.055 feet per second. So our This is a very simple problem. We're looking at power in, which is right here. It's power in. And why we couldn't solve it, because we didn't have power out. This is power out right here. So to find the solution to this, we're going to find the power in, power out. So what is power in? Power in is equal to 1 GPM times 1500 pounds force per inches squared divided by 1714. And we're going to get a power in of 0.875 horsepower. And this is hydraulic horsepower, so power out be mechanical horsepower, and it's going to be 4,500 pounds of force times 0.055 feet per second. And we're going to divide this by 550 because we've got to do that for horsepower. We get 0.45 horsepower. So to get overall efficiency, I'm just going to do efficiency of the system. It's going to be equal to our power out, which was 0.45, divided by our 0.875. These are both horsepowers, so they should cancel, and we're going to get 51.9%. Absolutely horrible efficiency. If you are using this cylinder, you probably need to look at getting a new cylinder. The reason why we didn't do mechanical and volumetric efficiencies is, again, because this problem is messed up. So we're not going to do that. You could figure them out with the inches, but I think what you find out is you have, like, again, messed up problem. I need to fix it, but moving on. So in this case, we have an electrical, for example, we have electrical motor supplies mechanical horsepower to drive a hydraulic pump. You measure the voltage to be 440 volts. That's weird. That should be 480, but we're going to go ahead and leave it at 440 at 13.63 amps. So hydraulic system is lifting 1,000 pounds force, 10 feet per second. What's the efficiency of the system? Okay. Well, in this case, we can find electrical horsepower. So I'm just going to do power in is just going to be our 440 volts times 13.63 amps. And that's going to give us a power in of 6,000 or so watts. Okay. To get the horsepower, we're going to multiply. There are 746 watts per horsepower. So watts cancel, we're going to get something like, let's see here. Oh, actually I just wrote down, so let me double check here. Divided by 746. This is going to give us 8.04 horsepower. Okay, so our system is lifting power out, lifting 10,000 pounds force times 10 feet per 30 seconds. So we can do that times divided by 30. And then we divide by 550. So that's going to give us 6. This all has to be divided by 550, by the way, to get the horsepower. So 6.06 horsepower. So power out. So to get our efficiency of the system, it's going to equal 6.06 horsepower divided by 8.04 horsepower. So divided by 8.04. We get an efficiency of 75.753. I should note that this actually goes to 75.3%. Remember, percent is where your decimal place. Two to the right or 2 to the left, depending on which way you're going. But so that's it. I apologize for the bad example. Actually, 2 bad examples, because you have 440 volts is uncommon voltage. You could have something wrong. But anyway, the actual examples do physically work out to be fine. So, but if you have any questions, let me know. There's plenty of other problems I posted that are probably a little better. But just let me know if you have any issues.